So, again, totally laughable. 10 minutes to talk about the basics of climate projections, models, emissions scenarios, and downscaling techniques. Here we go. So, why use models? Well, one good reason is non-stationarity in the climate system, which basically means that because of things like trends in temperature, it affects things like I just talked about, changes in snow hydrology and so on. So the past is no longer a good guide for the future, especially as we go out into the deep future. So models will provide more information than historical climate analogs, and we may end up in some novel climates, so-called non-analog climates, and models are going to be the only way that we're going to get to understand about those climates. So as my colleague Catherine Hayhoe is fond of saying, planning for the future based on the past is like driving down the road only looking through the rear view mirror. So what's in these models? The models use mathematical equations to represent all this stuff. The circulation of the atmosphere, the ocean, interactions between the land surface, the ice-covered surfaces, the atmosphere and the ocean, and the incoming solar radiation, and so on. And this is all done not with statistics, this is done with differential calculus to solve these equations for mass continuity, energy continuity, and so on, way beyond my pay grade. It's done for grid boxes for multiple levels in the atmosphere and way at depth in the ocean, all across the entire planet Earth. One of the big unknowns about the future is future emissions of greenhouse gases. For those, we use scenarios that are based on assessments of the literature and then supplemented by something called integrated assessment models. So these are plausible pathways for future emissions that don't really specify policy, but we could imagine different kinds of policy pathways that could lead to much lower emissions or putting the pedal all the way to the metal. So emissions are one of the main driving factors in these climate models. What does the output of the models look like? There are literally dozens and dozens of variables, atmospheric variables like the ones we're familiar with, temperature, humidity, precipitation, wind speed and direction, and so on. But there are also much more interesting things like cloud fraction and downwelling, long wave radiation. Then when you get into the oceans, we could look at the change in alkalinity and seawater pressure, and so on and so forth. How reliable is the output? A few rules of thumb. It's better for larger areas than smaller areas, and it's better over longer time spans than short time spans. We don't want to sort of measure a projection for a single day in the future. So better over time, over spatial scales of hundreds of miles than tens of miles, better for estimates of years rather than seasons or months or days, and especially useful for change periods, which is why I presented information earlier in those 30-year blocks. And also much more reliable for temperature, which is more spatially coherent than for precipitation, which doesn't mean that we throw all the precipitation information out the window. We just have to be more careful about those estimates. Another couple of rules of thumb is that multi-model averages are better than individual models because models all have their biases, and those biases tend to cancel out when we average things. We want to look at a range of models rather than individual models. There's no best model, but there are some groups that do culling and selection of models based on their performance looking back at past history. And here's an example of how the state of California does this. They look at particular factors for the entire globe. Do the models do okay? Well, some of them don't. We're going to remove these 12 and then move on to look at processes that are important for the western US, and then processes that are particularly important for California. And at the end of the day, they end up with 10 models that they use. you'd be well advised to work with an expert if you were going to do this kind of culling. There's also downscaling, trying to get information at the spatial scale that's consonant with the decisions that we make. So why downscale? One reason is that we might be interested in a particular small watershed. Another reason is that we might be looking at areas where there are very sharp contrasts in topography, and we want to take account of those changes in topography, which are pretty blunt in the original global scale climate models. So some reasons again are to take advantage of high resolution information for a particular context along coastlines in mountainous regions. And then because some of the process models where we want to learn about things like air quality or vegetation change or urban heat require more fine scale information. A little bit about downscaling methods. Basically what we do is we take output from the global models. We can either pass them through generally linear statistical equations or through a limited area, usually weather forecast type model that is a dynamical model and has all sorts of feedbacks and stuff. And then from either of those methods we get spit out the wonderful spaghetti plots with all the data. A couple of just very brief pros and cons. The statistical methods are inexpensive, but they assume stationarity in climate. The dynamical methods are based on physical processes. That's really good, but they're really expensive and you get limited runs of models, which makes it very hard to make use of the laws of large numbers to have robust statistics. How should we interpret the output from models? So here's one of my favorite rules of thumb. No model's perfect, but some models are useful, and when we average them, we might see some valuable information about the sensitivity of the systems that we're looking at. As I mentioned earlier, we might want to look at the magnitude of changes. We might want to look at the range of changes too and see the consistency of those changes over time. That's temperature projections for a particular spot. These are precip projections for a particular spot, and you can see there's a much wider range. I wouldn't want to count on this tiny change in the median, meaning that there'd be a big increase in precip. So looking at the whole range is important. And then based on some work by Catherine Hayhoe, we might want to interpret the output from models in terms of things that we care about, which might be drought, it might be dust storms, it might be the tracks of tornadoes. Well, we can stop right there for things like dust storms and tracks of tornadoes because we know that we just don't model those very well, and the global scale climate models aren't going to help much. So for those things, we have limited observations or limited ability to model, and the jury's still out. For other things, there's really robust trends like the ones that Kathy and I have shown for temperature. And some of the results from, for example, the National Climate Assessment tell us that we have high confidence in these projections of extreme heat or decreasing cold or extreme precipitation for parts of the country and so on. And here, the key thing is that these results are consistent with our basic understanding of how the Earth system works. They're also consistent with projected trends, and there's a lot of agreement among models. So one of those examples is about what future drought might be like in Texas as temperatures continue to increase. For other things, there's a lot of uncertainty, but we're pretty sure that if we use the past as our guide, we're going to get the wrong answer. So don't go out there without a guide. This is it's stuff that requires quite a bit of expertise to do. And there are many guides. I mentioned the NOAA RISA program only because I've been involved with it for the last 16 years. There are many other experts out there that can help if you want to dabble in this sort of thing. And then very briefly, sources of information. National Climate Assessment has a few chapters that tell you a bit about modeling. There's this interesting article in EOS from 2011 about guidelines for constructing climate scenarios, and then a more recent report put together for the Department of Defense that's actually written in pretty understandable language that discusses all of the sorts of things that I've mentioned in the last 10 or so minutes. And then if you really want to dive in there, you can look at a more technical report from the state of California. And you'll get this presentation, no doubt, on some website or thumb drive, and I've pointed out a few websites. Thanks for your attention.